can open up the room and just give us a few seconds after that.
Yeah, it's 11:30. Let's go ahead and do that.
Mr. Chairman, we're live.
Great. Good morning, everyone. This is Chauncey Goss. I'm chairman of the South Florida Water Management District, and we're really pleased today to be able to present today's Lunch and Learn on how meteorology is used in the management of water. Governing board members with questions, you can raise your hands during the presentation, and I'll call on you when you do raise your hand. As a reminder, today's Lunch and Learn is informative, and we're not going to be making any actions or taking any votes. At the end of the presentation, we will be taking public comment for the record. Staff will call your name to speak when we take up public comment, and if you're participating via phone, *9 raises your hand, and *6 mutes and unmutes you. Before I start, I'd like to remind everyone that the Lunch and Learn sessions have a 1 o'clock hard stop. So much of the district's operations decisions are influenced by weather, so it really doesn't come as a surprise to me that we have 2 meteorologists on staff. Although I tell other people that sometimes they act genuinely surprised. I think our meteorologists are really our unsung heroes, and I appreciate all they do. I'm really looking forward to this presentation. I'm going to ask Eric Schwartz, who's our lead meteorologist for the district, to discuss how the district uses meteorology to make real-time water management decisions, to manage the hundreds of water control structures in South Florida. Mr. Schwartz?
Thank you. Can you hear me okay?
I can.
Okay, great. I'll get started. My name's Eric Schwartz. I'm one of the meteorologists here at the district working in operations, and I'm going to provide some background information on the meteorological support we provide to the district, cover some of the meteorological tools we use in forecasting, and then finally discuss some rainfall patterns across South Florida. So let's get started. See if that... It's not advancing. There we go. Okay, as you probably already know, the South Florida Water Management District boundaries roughly correspond to the hydrologic boundaries, and therefore there's no rivers bringing surface water southward into the district. Therefore, all the surface water we're managing arrives as rainfall over our district. There's a good side and a bad side to that. The good news is we don't have some other entity using or polluting our water before it arrives in the district. The bad news is if it stops raining, we run out of water. Here's a map showing the zoomed in a little more on our district. And in theory, if a drop of rain falls over Southwest Florida Water Management District to our west, that water flows off to the west and southwest to the Gulf of Mexico. And a drop that falls off to our east, it's going to flow northeastward up through the St. Johns River. Rain that falls in the Kissimmee Valley is going to flow southward to Lake Okeechobee, and then the natural flow is to fan out to the south and southwest. And the water levels up in the northern end of our district, in the upper chain of lakes, typically are about 50 to 60 feet above sea level, and Lake Okeechobee is roughly 10 to 15 feet above sea level. And that's a decent slope. So this water is going to flow downhill. Water managers operate the system to control the rate at which it flows downhill, but it's going to move south. South of Lake Okeechobee, the landscape is much flatter. The water level of the lake, like I said, about 10 to 15 feet. And as you get to the southern end of the peninsula, water levels are pretty much sea level. And so across that 100-mile stretch, it's dropping from that 10 to 15 down to sea level. And that corresponds to roughly 1 inch per mile of slope. So that's pretty flat. And that gives water managers a lot more flexibility south of Lake Okeechobee. And they can actually move water uphill in some cases, either through pumping, or if water levels are high enough, gravity will let the water flow uphill. So moving on here, when the original Central and South Florida flood control project was designed, it assumed a certain amount of population control and development. The population of Florida has well exceeded that original population assumption. And I like to blame two factors, air conditioning and mosquito repellent. And I guess they didn't anticipate the prevalence of those two things. So in response to this increase in population and all the asphalt and faster, flashier runoff that comes with it, some of the ways that operation has adapted is by installing its communication and control system run by our 24/7 operations control center and by utilizing tailored meteorological forecasts. These two additions allow water managers to anticipate, monitor, and quickly respond to areas of heavy rain as they act to mitigate flooding issues. In order to manage the systems, our engineers require a forecast of how much can be expected. I put a quote in here from the greatest weather forecast issued in the history of man from NOAA circa 5000 BC. It oversimplifies forecasting heavy rain, but you get the idea. We're interested where it's going to rain heavily and how long is that rain going to happen and what's it's going to total up to. And we have 2 meteorologists on staff to help with that question. And we provide a tailored rainfall forecast known as a quantitative precipitation forecast, or QPF. It's different than forecasts you typically hear on the radio or see on TV. To quantify, to quantify the rain, we go beyond a 30% chance of rain or 60% chance of rain. We used to have a water manager here who would ask, what would I do with a 30% chance of rain? Open the gate 30%. And they need a little bit better detail than that. So instead, what our QPF does, the quantitative precipitation forecast, we break our district up into 14 areas and give a forecast of how much rain will fall on average in each area, along with a local maximum amount as we attempt to describe the personality of the rain a little bit. So instead of a forecast of 60%, we might give a forecast of an average of 1/2 inch of rain over a 1,000 square mile area. This represents a volume of water, and engineers can then go do what they were born to do, calculate. And so if water managers are in flood control mode, they can look at that volume of water that's been forecast and calculate if they need to move water to mitigate flooding. If we are in water supply mode, they can look at the volume of water and calculate if it will meet their water supply needs. The engineers use this information to then adjust their daily water strategy. So for our forecast, we generate a daily QPF for days 1 through 7 in both graphic and text formats. The examples are shown here on the slide. In addition, on the text forecast, we, in addition to the 24-hour rainfall amounts, we also give some information about the forecast reasoning and discuss some of the uncertainties involved in the forecast for the upcoming week. We recently have added a most likely range to the daily total to help water managers quantify this uncertainty. It's similar to the 25 to 75 percentile lines that you're probably familiar with on the Lake Okeechobee position analysis product. So, and these forecast products are posted on our website to help water managers coordinate with other agencies and municipalities, as well as for use by the general public. So looking at some of the tools we use while forecasting and help generate the QPF, we use many of the same tools you'll find in any meteorologic office that you may stumble into. For instance, we use radar data, satellite data, and observations of meteorological surface data. Examples of those are shown here on this slide. These are mainly helpful with near-term forecasting, but our water managers are interested not just what's going to happen over the next few hours or this afternoon. They want to know over the next few days what's going to happen. And when you get into longer term forecasting, we use a lot of computer modeling. and particularly from the National Weather Service, as well as the European Center for Medium Range Weather Forecasts. That's kind of a mouthful. It's the model that most people refer to as the European or the Euro. And to run these models, an analysis of initial conditions of parameters such as pressure, temperature, moisture, and wind is completed. That's shown on the graphic on top. That's analysis of current conditions. And then using math and physics, the computer models calculate how these conditions will change over time. 6 hours in the future, 12 hours, 24, out to 10 days, and sometimes out to 2 weeks, how that's going to happen. And that's what the graphic animation down in the bottom left is showing, is a 10-day forecast of how the upper level winds are going to be changing across the continental US. Florida's there down in the bottom right corner. So to come up with these analysis of initial conditions of the atmosphere, agencies all over the world sample the atmosphere twice a day with weather balloons. So yes, meteorologists still launch weather balloons. A lot of people are amused by that, but it's a pretty important step. The balloons are launched simultaneously at noon and midnight London time around the world. So if you can see it, it's like a big balloon. Instead of balloon drop, it's a balloon up all at the same time, twice a day. And sensors suspended below the balloon transmit data such as temperature and pressure back down to the launch station, and winds are derived by watching the balloon drift as it ascends. The computer then analyzes this data to come up with initial conditions. And it's much like sampling a sheet cake with a toothpick to see if it's done. There's a map on the bottom left there. The little red boxes are the launch locations across the United States and the Caribbean area, and gives you an idea of how spread out the sampling is. There's gaps in there. There's also some large data void areas, mostly over oceans. And that has given us some issues in the past, because the ocean area off to our east, that's the upstream area during the summer months. But fortunately, data is now being supplemented with satellite estimates as well as aircraft data. And that helps improve the initial analysis. And the European model is particularly good at this. And the initial analysis step is critical to forecasting, because as with all models, if you start with garbage and then calculate out forward in time, things generally don't get better as you go out in time. Instead, you end up with garbage squared as you do all those calculations. And all model forecasts have a element of uncertainty in them. A way to compensate for this uncertainty in computer model output is a technique referred to as ensemble forecasting. With ensemble forecasting, you can average together several different models which use different physics packages. The reason the different models have different packages is the atmosphere is very big, very complicated, and assumptions and simplifications have to be done in order for the computers to complete the required calculations in a reasonable time frame so that it's usable. If the model takes 3 weeks to run, it's not going to help us with this afternoon's forecast. So, but then by averaging several model solutions together, you can take advantage of these diverse calculation techniques. Another type of ensemble forecasting involves running the same model, but many different times with slightly different initial conditions. And this is helpful because it compensates for the uncertainty in the initial conditions of the atmosphere. We really can't know all those initial conditions at high resolution and with high certainty. So by making small changes and rerunning the model, it's like a sensitivity study to see how these small changes influence the final calculation. And it helps quantify the uncertainty of the forecast on any given day. If you by changing those initial conditions, it doesn't really change the final outcome, then confidence would be high. If by tweaking those initial conditions, you get widely different solutions, then our confidence is much lower. And a couple of examples of how some of this ensemble output can be utilized are shown on the slide here. The top one shows 6-hour rainfall at Miami for a 2-week period from the 51 ensemble members of the European model. And time changes from left to right across the graph, and each horizontal line represents one of the 51 model solutions, and the colors represent the 6-hour intensity of rain. And you can see there's a lot of variability in these ensemble members. Initially, the rain over the first few days, it has to do mainly with intensity. But then as you go off to the right, you see there's some timing differences where on some days there's no rain and the rain might be a day later than what some of the other models are predicting. And then looking in the bottom left, the 31 postage stamps down there are 60-hour total rainfall across Florida. Each one has the peninsula of Florida and also the panhandles on there, showing the contour of different rains. And some days, or some of the runs have very heavy rain, and some of the runs have lighter rain. And in both cases, both ensemble cases, the right answer is probably hidden in there somewhere. The problem is we don't know which one it is, because we don't know which one of those initial conditions were actually the correct one. And the idea is that if you average all 51 or 31 solutions, it's been shown that that's a better predictor than just taking a random solution and deciding, I think this is the best one and running with it, unless you have a very good reason for picking one of them. The average ends up being a better forecast. So going to show another example here of ensemble forecasting. And we're looking at the 51 solutions from the European ensemble members and how it interprets change with tropical cyclones. On the left-hand side, we have 2 still pictures showing Hurricane Dorian from 2019, the 2-day forecast and then 4-day forecast as Dorian was approaching our area. And you can see there on the 2-day forecast is a pretty good cluster of position. There's 51 little L's on there if you zoom in and look at it. And you can see there's a decent clustering off to the east of the Bahamas. But by day 4, they're starting to spread out quite a bit more. So that scatter gives you a feel for the range of possibilities. And so while we would have decent confidence in the 2-day forecast, we would have much lower confidence in the 4-day forecast. And I think it's a helpful tool to emphasize how far out in the future in any given case we feel comfortable with the forecast. Sometimes the forecast is very confident out 4, 5, 6 days in the future. Sometimes it starts falling apart after about 12 hours. The animation on the right is actually from this morning, and it shows the same 51 model runs with different lows, all drawn with little red L's and the pressure in black with it. And when the graph starts, you can see Hurricane Zeta in the central Gulf of Mexico. It'll restart here. There it goes. And there's really good agreement, taking it up. The confidence is pretty high that it is going up to Louisiana. That's why we're confident it's not an issue for us. It's actually more of a drying influence for us, and it should not be a threat of rain or wind. And this animation runs out 2 weeks into the future. Now it goes out to 360 hours. And what you start to see during the second week are a bunch of little L's that start to show up down by Nicaragua in the Southwest Caribbean. But initially they're clustered a little bit, but then then it looks like somebody kicked an anthill and the L's just start running off in every which direction. So that's a sign there's not a good consensus of what's going to happen with that. But the good news is none of the 51 solutions bring the system directly across us. We might be influenced by some of its moisture, but it's not a threat to us. And we could have fairly decent, right, be moderately confident of that, as much as you can be 10 days out in the future. So in addition to quantitative precipitation forecasts, water managers are also interested in how much rain has actually fallen. And to answer that question, we utilize roughly 300 rain gauges from multiple agencies across our district on a daily basis. The map on the left shows the various locations of these rain gauges, and the colors represent the different agencies and sources for this information. And we use this, we do a weighted average of these rain gauges to come up with rainfall in the different forecast areas of our district and the district as a whole. And that's the source of the data for the district maps, comparing monthly or seasonal rainfall to the historical average. Those type of graphs they're shown on the right. Now, of these 300 gauges, 200 of them are ours. And so now the map, I took away the other agencies. And these red dots are all rain gauges maintained by South Florida Water Management District, and that report back in near real time, meaning that we get them at least every 15 minutes through the day. And these rain gauges help our engineers monitor where the rain is actually falling. And they do an excellent job of describing how much rain fell in an 8-inch cylinder. And there's a rain gauge there on the picture on the right. But they don't necessarily describe what happened a mile away, and they often tell you nothing about what happened 5 to 10 miles away. And when you look at the network map, you see there's large gaps out there, and some of these gaps are unavoidable because of land use or siting issues. To fill in these gaps between the rain gauges, we can use radar data, and radar data does an excellent job of giving a spatial depiction of the rainfall and giving a general idea of areas that receive light, moderate, or heavy rain. But it doesn't really give a precise estimate of how much rain fell at any given spot. So on one hand, we have a rain gauge network that gives very precise values and a coarse resolution. And in the other hand, we have radar data that gives high resolution description of general rainfall amounts. And neither one of these really meet our needs. So by combining these two sources of data, the district generates a product that is less wrong than either method by itself. And here's a couple of graphics showing what the output of that looks like. The district has a contractor that combines our 15-minute precise rain gauge values with the high resolution radar data, and we come up with a 2 kilometer by 2 kilometer grid over the entire district every 15 minutes. And we've called this product Raindar, since it combines the rain gauges with radar data. And the Raindar data can be averaged over any basin that the water managers need and tracked over various timeframes to help them monitor the input to the system. And that the graphic on the right shows how we go from the high resolution pixels to the individual basins that water managers are tracking. And our near real-time rain gauge data and the Raindar data are posted on our website, and they're also available through the district's historical database, DB Hydro. So hurricanes are always a very exciting weather feature, and it's a reason a lot of meteorologists decided they wanted to become meteorologists, and some non-meteorologists who enjoy tracking them. And when we have a tropical cyclone threatening the district, the meteorologists here at the district continue to produce our QPF products and the Raindar products that we do all year round. They just get a little more colorful. In addition to these products, we also provide guidance to the district through the district emergency manager to help the district prepare for potential winds and heavy rains that are associated with such an event. So now I'm going to move on to talk a little bit about rainfall patterns over the district. And the peninsula of Florida is near a latitude that globally has a fair amount of sinking air. That's because air rises over the equator with heating and then generally sinks back down about 20 to 30 degrees of latitude, both north and south of the equator. And there's a lot of desert regions clustered around this range, both north and south of the equator. the desert areas such as northern Mexico, the Arabian Peninsula, and the Saharan Desert in North Africa. These are all in a similar latitude range of where the district is. But even though the district falls in that range, we're also surrounded by water on three sides. And this contributes to sea breeze thunderstorm activity that you can see forming up there, a satellite loop from July showing how with the heat of the day, you start to get a little bit of cloud cover, and then it starts to boil up a little bit, generating thunderstorms, and they start interacting and bumping into each other and fill the peninsula with rainfall. And these afternoon thunderstorms provide a significant amount of rain during our annual wet season. And it's worked out well for us. Australia, if you look on the graphic on the left, the top left there, Australia is in a similar zone in the southern hemisphere, and it's also surrounded by water, actually on all four sides, but it's a much larger landmass, and it's too large of a landmass for the thunderstorms to completely spread across it each day like it does across South Florida. And people who have modeled sea breeze development have come up with an optimum width of landmass for sea breeze thunderstorm development of about 100 miles. And that's pretty close to what the peninsula of Florida is. So we're optimized for sea breeze thunderstorms. And that's good. That's, since we depend on water that falls on our district, it's pretty important that we're geared up to produce it. And we get nearly 3/4 of our annual rainfall during that 5-month period of mid-May to mid-October, when thunderstorms dominate our weather. And here's a plot of the average monthly rainfall over the district. We prefer the term historical rainfall average or 30-year average over the term normal, because it seems like we never really get normal rainfall. It's more abnormal. It feels like we're either in a drought or a flood, feast or famine. But we can calculate the historical average, and it does show a clear pattern of a well-defined wet season for about 5 months and a dry season for the remaining 7 months. And wet season months produce 6 to 8 inches of rain each month, as compared to roughly 2 inches per month during the dry season. And we had a water manager here who preferred the term drier season over dry season, because he would point out it still rains during our dry season, just not as much. And we can still get heavy rainfall events right in the middle of the dry season. And so our wet season is dominated by the daily sea breeze thunderstorms, and there's periodic heavy rainfall events mixed in there. Our dry season is characterized by more episodic rain. Sometimes it's heavy, associated with systems such as fronts or lows, and those events are separated by periods of little or no rainfall. And so when we look at these heavier rainfall events, one way to classify them is look at the days that produced at least 1 inch of rain across our district on average. And we've referred to these region-wide soakings as big rain days. And here's a graphic showing the observed number of big rain days by month since 1991. And we average 5 to 6 of these per year, and the most likely month of occurrence is June. And but as you can see, the big rain days occur year round, and we get an average of 2 or 3 of them during the 5-month wet season, and 2 to 3 of them on average during the 7-month dry season. So while less overall rain does fall during our dry season, water managers still have to respond to big rain days during that drier time of year. Hence the phrase, the drier season, not the dry season. So nearly 3/4 of our annual rain occurs during our wet season. And this rain is critical to the district's water supply. I mean, it's 3/4 of it. We're like squirrels collecting acorns during the summer months for the upcoming winter when it's raining in the summer. But it's a great unknown how much rain, total rain, will fall through the course of the entire wet season. And sometimes as a wet season is approaching, we may be asked to forecast how much rain the wet season will produce. And in response, we point out there is no demonstrated skill at predicting total wet season rainfall. So we don't issue such a forecast. Instead, we're focused on the daily rainfall amounts, looking out as far as a week, sometimes 2 weeks if we have a little bit of, if uncertainty drops down and we feel comfortable making that forecast. But even though we can't tell you how much total rainfall is going to fall, there are some things we can tell you about each wet season. We can tell you that there will be a wet season and that it will produce roughly 3 feet of rain plus or minus a foot. And yeah, at first glance, that kind of looks like a worthless piece of information, but it does tell us some important things. First of all, we will have a wet season. We've had one every year. And this daily beat of afternoon thunderstorms will produce about 2 feet of rain at a minimum. That's an advantage we have over some other parts of the country. We know one is coming. Sometimes when people have a dry season or a drought, they don't know when the next significant rain is going to arrive. We know we will have some every summer. And by having that plus or minus a foot, that's a rough number, but it's relatively easy to remember. It sets some boundaries on what has occurred historically. The daily rainfall during the wet season is typically enough to meet short-term water needs during the summer and sometimes exceed those water needs. However, we need to get more than that minimum 2 feet to start building up storage for the next year's dry season, like the squirrels saving the acorns. And here's a timeline of how the wet season historically has unfolded. The tail end of the dry season in April on the left-hand side of the screen, and moving it forward in time to the right. There's a transition period to the wet season. Then the wet season continues June, July, August, September, before transitioning back to the dry season in the fall. And looking back at the last 30 wet seasons, the average start date is May 22nd, plus or minus 2 to 3 weeks. And then the average end is right around October 12th, plus or minus 2 to 3 weeks. And if we've had a really dry spring, an early start to the wet season is often viewed as a welcomed relief. However, a late end to the wet season helps us prepare for the next spring. And this later example of a late end is the boat we're in this year. And with the outlook of below average rain, that could work out favorably, hopefully. So this is our monthly rainfall graphic again, but I've added a line overlaid showing the monthly Lake Okeechobee evaporation values. And evaporation rates vary through the year, just like rainfall, only in a different phase. The main contributors to evaporation rates are things like sun angle above the horizon, length of day, cloud cover, temperature, humidity, wind. All these vary through the year, and you end up with a curve similar to rain, but offset a little to the left there when you look at it. And so looking at evaporation rates over Lake Okeechobee, they vary from a minimum of 3 inches per month, November through January, and then rise up to a maximum of 5 to 6 inches, March through August. And our district has the benefit that much of our dry season occurs during periods of seasonally low evaporation rates. And wet season thunderstorm rains often mask the high evaporation rates during the summer months. Some places, such as California, are in the opposite situation. They have high evaporation rates during their summer dry season and low evaporation rates during their winter wet season. So out there, their evaporation rates amplify the extremes of wet and dry, as opposed to here in South Florida, where they tend to damp it out. The big exception to this idea occurs in March, April, and then May until the wet season kicks in. Evaporation rates start to ramp up during these months as the sun gets higher in the sky, the days get longer, but then our humidity and cloud cover stay low until the wet season begins. So we start having higher and higher evaporation rates. And even with normal rainfall during this period, evaporation will outpace rainfall. So March, April, and early May is often the very dry season. So it's not really it's a little more dry than the dry season overall. And if we have a long-term rainfall deficit over our area, it will become most apparent from February through May when those evaporation rates ramp up until the wet season starts. And not surprisingly, water demand also increases during those dry times due to the high evaporation rates. And this increased water demand can also amplify the water shortage situation. And looking at seasonal forecasting, it's always tricky. As I said earlier, there's no demonstrated skill at predicting rainfall totals for the wet season. However, there is some skill at predicting seasonal rainfall during the dry season, just not every year. And fortunately, we do have a clue which years we have a better chance of getting those forecasts right. There's a fairly strong connection between El Nino, La Nina cycle and rainfall over our district. A lot of people are familiar with that. Some specifics on it. The most significant correlation there is during a 5-month period of November through March. And it's most pronounced during moderate or strong El Nino events. And El Nino events occur on roughly a 2 to 7 year cycle. It's not a nice normal up down. It's not like sunrise, sunset. It's variable. And what happens in a typical El Nino event, you get an increase in ocean temperatures over the equatorial Pacific, and the part of the Pacific Ocean that's near the equator. And that increases moisture and energy in the atmosphere, which is transported eastward and can affect the district's weather. The opposite of this scenario is La Nina events, where you have cooler ocean temperatures, fewer episodes of moisture and energy streaming across the district. And these effects are, like I said, most pronounced November through March, and the stronger the event, the more pronounced the effect. And it's very important not to oversell El Nino conditions and La Nina conditions and the effect on the district's rainfall when we're in a weaker El Nino event. Because this erodes confidence in our ability to predict the effects of the stronger events. So looking back at some past events and to highlight the importance of the strength of El Nino and La Nina events on the potential rainfall here in South Florida, here's a graph that's comparing November through March monthly rainfall during various El Nino events since 1950. And it probably needs a little explaining. It's a little busy. What we did, we looked at monthly rainfall for those 5 months, November, December, January, February, and March, and separated those months into categories of very dry months, less than half a normal rain, and very wet months, which 50% above the historical average. Remember, the dry season months generally produce about 2 inches per month. So very dry is below an inch. Very wet is above 3 inches, and the remaining 1 to 3 inches were lumped together as a moderately dry to moderately wet category, or the Goldilocks category, where it's maybe a little wet, maybe a little dry, but not too bad. The first column on the left shows the distribution of occurrence of these 3 categories for all years. And we can say that knowing nothing, and that's something I'm familiar with, we would expect about half the months, 53%, to be in that green Goldilocks category of not too wet and not too dry. Just under 1/3 of the months, 31%, are very dry. Those are shown in the dark orange, the very dry. And the remaining 16% are very wet, shown in blue. So that's the distribution in any given year, picked at random. That's what you would expect in the season coming up. Looking at the columns to the right, they show how that distribution changes for those same 3 categories as the strength of El Nino and La Nina changes. And the strength of the events are labeled below each column. And looking at the middle column, near the middle of the grouping there, the neutral to weak conditions column, we say there is not much difference from the all years column, where it's 49% or at the Goldilocks, 40% very dry, and 11% wet, very wet. And so these are the events where it's not really a good idea to overemphasize the possible effects of a weak El Nino or a weak La Nina on our monthly rain, because it's really not much difference, no noticeable difference really from what we would get just typically. But as you move to the right from that neutral weak and move through increasing intensities of El Nino, you see that the very wet months become much more likely. 23%, they're shown in blue, circled in red, 47%, and even 60% when you get out to the very strong El Ninos. And as you move to the left from the neutral weak column, you see that increasing intensity of La Nina, the very dry months become increasingly more likely as well. 43% and 60% down there in the dark orange as you move off to the left. So in these strong La Nina and strong El Nino months, we see a fairly strong relationship. Those are the situations where we feel we can have some meaningful rainfall outlooks. But before we get too excited, I'd like to point out that even in those strongest events, it's still only 60% of the months that ended up being either very wet or very dry, depending on the strong El Nino or La Nina. And 60% success rate is not that great. And in fact, when I went through school, that was a D. And so I think we should be trying to do a little better than that. And, but so the stronger events, they still provide some reasonable guidance that I think we can use. So to improve our success rate a little bit better, instead of looking at which category is the most likely category to occur, if we start looking at which category is the completely wrong category and avoid picking those categories as what you hope is going to happen, or make a decision that counts on that kind of monthly rainfall to occur. So instead of wet during La Nina events, if we choose not dry, and instead of dry during La Nina events, pick not wet, meaning during those stronger El Nino events, not dry combines the very wet months with the Goldilocks months, and you get down to a 5 to 13% chance of being wrong. And during the stronger La Nina events, a net not wet forecast gets you down to 7% or lower chance of being wrong. And an 80 to 90+% success rate sounds like more of a passing grade. So to sum it up, when it comes to El Nino and La Nina events, the connection to our rainfall is mainly during moderate and strong events during the months of November through March. And it's often beneficial to avoid the wrong answer as opposed to trying to pick the best answer when we're trying to figure out how much rain for our upcoming season. So now brings me to my final slide. Here are a couple of seasonal outlooks from NOAA for the first part of this coming dry season, November through January, and then January through March. There are moderate La Nina conditions that have developed over the equatorial Pacific, and they are forecast to continue through our dry season. And as we know, La Nina conditions are associated with below average rainfall November through March. Not surprisingly, this is what NOAA depicts in their outlooks right now. However, when people look at these graphics, there's a tendency for them to look at that, and especially with that brown color that's selected, people think it looks parched without a drop of rain over that entire 5-month period. But remember, what we learned in these previous slides can help here. There's definitely an increased chance of some very dry months this dry season, not underplaying that. But we could still also expect 1 or even 2 of the months to be near the historical average. So that would be beneficial to us. The timing of this rainfall, however, is critical to how beneficial it is. If it were to occur early in the dry season, when evaporation rates are low, it's just going to mix in with the residual water we've already stored from the previous wet season. If it were to occur in March, when the evaporation rates are starting to climb, that would be the most beneficial time. And unfortunately, predicting the specific months like that is beyond our abilities at this time. So historically, the best path for success over the coming dry season is to avoid counting on the months being above average rainfall. And that wraps up my presentation. I will hand it back over.
Oh, thanks very much, Eric. That was really fascinating. I wish everybody who lives in South Florida, or I hope everyone who lives in South Florida has the opportunity to watch that at some point. It casts a new light on what we look at every day when we look out the window. I'd like to open this up to board members. If you have any questions or comments for Mr. Schwartz, please raise your hand now and I'll call on you. Mr. Olipich.
Thank you. Very interesting, Mr. Schwartz, Dr. Schwartz. Thank you very much. I have one simple question first. I believe that hurricane season goes through November 30th. Why is that when the dry season is starting in November?
That's a good question. Our wet season isn't really tied to hurricanes. It's tied to those sea breeze thunderstorms. And so typically during the month of October is when we start getting cold fronts moving down. We start getting stronger winds aloft, and it kills off the sea breeze thunderstorm cycle. So hurricanes still do continue to develop. Most of them stay away from us. Our prime time is from mid-August until late October. But occasionally we have had mainly a tropical storm that could threaten us or even move across us in November. And so it is kind of odd to have a hurricane right in the middle of the dry season, or a tropical storm right in the middle of the dry season, but it happens. And I think that flows under those heavy rainfall events. And I can think of a fairly big one, Tropical Storm Mitch, that moved across in 1998. The first part of November was pretty wet, but our wet season had long ended by the time it came through.
It's really interesting. I've always thought that hurricane season was what defined wet season, like for fertilizer ordinances and such with the town. That's interesting. And the second thing, if you don't mind going back to slide 26.
Yes.
I mean, very helpful, but I feel like I have a spaghetti chart in my mind after listening to you talk, kind of. Is there any way to simplify your message? Was it kind of like moderate La Nina? We have pretty good ability. You have pretty good ability to do predictions, but not always. I mean, how could you say that in terms for an 8th grade class, or for just simple, for like me, people trying to just have a general way to remember it? I get all mixed up, even with like La Nina and El Nino,
Yes, I know what you mean.
It gets to be a lot of twisty, turny terms. What's an easy way to remember your message for slide 26, please?
Well, I tried to sum that up in the text up at the top, that
Okay.
the strength of the event matters. So it's really those moderate and strong events, and which months primarily we see the effects, November through March. And then also, if we look at La Nina on there, so you have the moderate La Nina and the strong La Nina events, and you see the wet months, that 7% of those wet months, or 7% of the months have been very wet during November to March, which is half the average. And then as you get to a strong La Nina, we've actually never had a very wet November through March, or any of those 5 months during a strong La Nina. So it becomes increasingly unlikely. So I guess I might be able, instead of showing the distribution, I could maybe change that to show the likelihood historically of each of those occurring, and maybe that would clean up the slide a little bit.
No, it's a nice.
I'll think about it and try to
I-
come up with something that's
Could
a
you
little
try
better.
to have, no, it's a great slide. And for most people, it's probably the best slide. My brother would have it on his wall. Give me two sentences or one sentence that explains the high point of this slide.
That the intensity of El Nino and La Nina matters.
Okay. Okay,
That's
that's good.
That's probably sums it up, because like I said, sometimes we have weak ones and people say, oh, we got El Nino, it's going to rain all winter. And then it doesn't, but it was just a weak El Nino. And then the next time we have an El Nino and it's a very strong one, like 2016, and we're saying, well, we're going to have a lot of rain. People say, that last El Nino didn't produce anything. And it's just like, yeah, any situation, there's variability in the strengths and their influence.
Okay, and those strengths can be changing too, right? Like just because today it's moderate doesn't mean it's not going to get strong or less.
Right. You're right. There's been some winters where we have a El Nino starting to occur and it fizzles by the time we get to January or February. And then we don't get the full effect for the whole time frame. And other times, like right now, we've stepped into the moderate category. If it were to intensify the La Nina, the drying influence, it could become more significant if it became a strong La Nina. So it's kind of a forecast that depends on another forecast. And so it's, yeah, and so now you are getting into uncertainty squared, because there's errors in the forecast of how El Nino and La Nina will evolve each winter or each year. And then our dependence of rainfall on that also is another forecast. So it's a two-step, and each one has its own uncertainty.
Very helpful, and so appreciate what you do. And I look at the rain slides a lot and have a lot this year with our 20 inches of rain, I believe twice during 2020 here in Sewell's Point, Martin County.
Yes, it's been a busy year.
If you're through, Mr. Lipich, we'll go to Mr. Steinley.
Hi, Eric. Thanks so much. Great presentation. So, I mean, obviously a lot, almost everything we do from a district perspective will rely to some degree on weather forecasting and planning in advance. So I'm just wondering, have you seen the margin of error of the forecasts that we use, that people use in general, increasing relative to more extreme climate events or warming scenarios? So I'm wondering, over the past 5-10 years, has the margin of error increased? If it hasn't, or if it has, do we expect it to continue increasing? Because obviously that plays a significant part into our planning process.
Well, I guess there's two ways to look at it. One, the forecast skill has been improving over the decades that I've been forecasting, and that's primarily related to computer model improvement, because we have better computing power. So remember, I mentioned there's assumptions and simplifications that have to be made when you're in the models. And as computing power has increased, we've been able to actually put in formulas for the physics instead of just making an assumption. And that's dramatically improved our ability to forecast sea breeze thunderstorms over the peninsula of Florida. When I first started in the 1980s, that was a pipe dream to be able to model those. And now we have very high resolution models that can do that. Also, there's better input into the models. Like I mentioned, using satellite data and aircraft data. So it's filling in the data voids. So our forecasting on a daily basis and out to a week and even out to 2 weeks has improved dramatically. And I think if you go back, you can see it. If you think back on TV forecasts, they used to just give you today, tomorrow, maybe the third day. Now, you can look on your phone and it's taking you out to 7 to 10 days oftentimes. on your app on your phone. So 7 to 10 days was not going to have much accuracy back then. But then when you're talking about the uncertainty, if you're looking at what average is considered, the historical average, and then how many times we go outside of that bounds and go to a more extreme event, that'd be a different question. And I think in some situations, some of the rain intensity is being shown to have more frequent extreme events, things particularly from tropical cyclones like Harvey in Houston and Florence up in South Carolina a couple years ago, with slow moving tropical cyclones dropping feet of rain, not just inches of rain, feet, 3, 4, 5 feet of rain. And so those types of extreme events appear to be more frequent. Because sometimes when you look at increased frequency of events, people say, well, we just have more rain gauges collecting the data now, so that's why we're seeing these events. But you weren't going to have a Harvey in Houston or a Florence in South Carolina and somebody not notice it. It was a multi-county event. So, and those type of events seem to be increasing in frequency. I mean, not to put
So that helps. So if I understand correctly, the technology is improving, it's reducing our margin of error, it's improving our forecasting, even if weather events are more volatile. But then if I'm understanding your second comments, because there are more extreme weather events, is our ability to forecast the extremes impact, has it too been improved? I
think since the modeling has improved, and like I was saying with ensemble models, showing the likelihood of some of that when the models are going for very high rainfall. It used to be they'd run one model run each day or twice a day. And when you would get the output, if there was some bad initial data that got in there, somebody, put in Celsius instead of Fahrenheit and it didn't get caught in the QA/QC, you could get some very erroneous information. And so you'd get an extreme event and that was never going to happen. And so when you get that one run and you say, well, was there bad data? Now with the ensemble, if a fair number of the ensembles are going for very heavy rain, or if it's a tropical cyclone, if they have it slowing down and stalling over an area, and most of the solutions are leaning that way, then I think we would be willing to put that forecast out because our confidence in the model, we can quantify that uncertainty a little bit better now.
Thanks very much for that. Mr. Bergeron?
Yeah, thank you, Mr. Chairman. Can you hear me okay?
Yep.
Yes, sir.
Okay. Well, Jay kind of went over some of the things I was going to talk about, so I won't repeat any of that, but I'd just like to compliment our staff. Tremendous presentation, and I can tell you the technology has changed so much from, I can remember back in 1947, the first hurricane I experienced, we didn't even know it was coming. And so there's been an awful lot of change in my lifetime, and tremendous tool in order to manage, flood protection and water supply and compatible water levels with the environment. Totally amazing that can help us into the future. So thank you for your presentation.
Thank you. You're welcome.
Thank you, Mr. Bergeron. Colonel Roman.
Yes, thank you, Mr. Chair. And I want to thank Eric. Your presentation was just so informative and interesting. Who knew weather could be so exciting? But I mean, it's always exciting when it's raining or not. But I think the information that you shared shows how there's so many variables that are impacting on the amount of rain and how it falls and how it's distributed. It's very fascinating. That prompted me to ask a question regarding this evaporation. Now, on your slide that you talked about district rainfall versus evaporation, I have two questions. One, what impacts, and again, with the Jackie Thurlow-Lipich approach, a sentence or two, what affects the evaporation rate? And do we monitor evaporation only with Lake Okeechobee?
Okay, well, first we have evaporation equipment. There's monitors, sensors across the district. It doesn't vary as much as rainfall. So we don't have 200, they're called pans. They're basically pans of water, and they look how much evaporated out in the day. It's more along the order of 10 roughly. And that's enough to give us an idea. We can also estimate evaporation based on things such as wind and temperature. There's formulas to come up with that, and also come up with something, evapotranspiration, which is a mouthful, but that's how water evaporates up through plants and vegetation. And so there's calculations that our scientists can do for that. And you were asking the main thing, the overwhelming factor in evaporation is the sun and the seasonal change. So when the days are short and the sun is low in the horizon, evaporation is low. When the sun is up high and we have long days through the summer, evaporation rates are high. That's the number one. But then some other factors, and I rattled them off really fast. Some things, how much humidity is already in the air. If it's very dry, it evaporates quickly. If it's humid, like the middle of the summer, it won't evaporate quite as fast. And how much wind is blowing. Because you think about it, if you have a little pan of water and there's new air flowing across constantly, it's going to evaporate faster than if it's stagnant air and the humidity is increasing over that little pan. So those are the main, and then also cloud cover is another big one. And that's, you know, when you go out and cut your grass, you know immediately that it's hotter. The sun is more intense on you on a sunny day than it is a cloudy day. And so the cloud cover has another factor. But the most important factor is the seasonality of it. Those other factors are more on a day-to-day basis. The seasonality being the sun and how high it is in the sky, how long the days are.
To follow up on something that Mr. Steinle mentioned in terms of climate change, in the area of global warming, as temperatures increase, would you see more evaporation over time? Would that be enough to impact the balance between the rainfall and the evaporation?
That is one of the factors. As you increase temperature, if we have a warming planet, you would see higher evaporation rates. And I think the biggest effect of that would probably be felt in that very dry season from March, April, and the first part of May. And if we're in a drought situation where it's not raining a lot and we already have high evaporation rates, during that time frame, if evaporation rates increase a little bit, it will compound the effects of a dryness or even a drought during those month periods. During the summer, there's usually enough rain to account for that evaporation and even high evaporation times. So I think the biggest impact will probably be in that spring, very dry season.
Thank you very much. Really appreciate it.
Thanks. I've got a quick question for you, and it hits a little bit on what Mr. Steinle was asking, and it has to do with what I guess I'd call predictive meteorology. And I'm assuming, and I'm sort of excited about the fact that it's got to be getting a little better because we've got things like artificial intelligence and machine learning and quantum computing and better satellites. And you alluded to that. Your modeling is getting a lot better. And I just wanted you to maybe touch on that a little bit. And I'd like to know if there are any tools that you really would like, but you don't have now that would help you.
Well, I think in terms of tools, I mean, we're not going to run our own ensemble model here at the district. I mean, they have entire agencies running those, but then particularly the European model has some very good output. And we're actually working right now to come up with an affordable method to get some of that ensemble forecasting. Because one of the no man's land of forecasting for most of my time in weather has been the 2 weeks to 30-day time frame. Because computer models and just looking at the initial conditions and using the physics and math to calculate what's going to change, chaos starts to break in usually by the time you get out to 2 weeks, and it starts being very chaotic, the solutions, and it's harder to track. Beyond 30 days, statistical models have traditionally been the main use or the main source of good data there, but you need enough of a time frame out in the future for the statistics to pan out, because it's one of those things, where you say, 9 out of 10 times it'll rain in this situation, and the first one fails, and you're like, oh great, that was the 1 out of 10. You're supposed to get one, but if you get it right up front, it ruins everything. So you need some time for the statistics to play out. But now some of the modeling, and particularly from the European model, they have models that run out 46 days in the future, and they're not completely worthless. They're actually providing some useful information, and some of that information might be beneficial for short-term planning of Lake Okeechobee or other water levels in our district. So we're looking into what type of source there could be that's affordable to get that, because the European, the ECMWF are their initials, you have to pay for their data. They put a small amount of their data out there for free on the internet, kind of a teaser to get you to see how good their model really is. But then if you want to see everything, you have to pay for it.
Well, we've seen over the last couple of hurricane seasons that their model seems to be a little better than some of the other ones out there. And I would certainly encourage you to get what you need, because it's so important to us. I mean, if you have that extra couple of days and you have that extra knowledge, I'm certain, I'm not telling you anything you don't already know, but from a water management standpoint, that's gold. So that's worth it. Mr. Olipich?
Thank you for noticing my hand went up again, Chair Goss. Dr. Schwartz, Mr. Schwartz, could you?
Mr.
Mr. Thank you. Would you please go back to the slide that Colonel Roman had you have up? I couldn't see the number. It was the, yes, thank you very much. So with all the things that you're talking about, I'm just curious, do you end up sitting down with other water managers at the district, maybe operations, and start talking about, the lake level and where we're going from here? It's kind of, for me, this is a little bit of a strange conversation, or it's just the nature of everything, that here in my community, and also on the West Coast in Fort Myers, the estuaries are taking tremendous amounts of discharge water from Lake Okeechobee. I think the lake is at 16.36 today. So, but it's interesting, and I've noticed it on the periodic scientist calls too. People are worried about there not being enough water, and we're getting dumped on, and we're already talking about there not being enough water, and you're like, oh my gosh. So how do you start to blend your modeling, like this slide, with what happens with operations? I think they have to follow or LORS, and I think that's 15.5 or something, the level of the lake at a certain date. Or could you just talk about how that's blended, or do you have nothing to do with that, and that's totally a policy thing that comes through the district through the Army Corps?
We do interact with the group that puts together recommendations for Lake Okeechobee, and seasonal outlooks do factor into those. And we try to emphasize to only follow those during those stronger and the moderate and strong El Nino and La Nina events, the seasonal outlooks from NOAA. And then in terms of the meteorologists here at the district, we provide input for week 1 and week 2 outlooks of, because they're looking at inflows to the lake, the antecedent conditions, how moist it is ahead of time at the groundwater and water levels. And then, so we have kind of the short, what they consider a short-term forecast is 1 to 2 weeks. And then beyond that, it becomes NOAA's seasonal outlook has an influence on that. So it is factoring in through that.
And do you feel like
So,
your predictions tie in pretty well? The evaporation you were speaking about with Colonel Roman, and where it ties in with the LORS. I know that schedule will be updated, but with LORS, I mean, it's very sensitive, and it's the heart of the rub in the South Florida Water Management District for a lot of people who are taxpayers, because always trying to find, that Goldilocks situation for the lake, for the people, for the estuaries, for the birds, for the agriculture community. I hope that you have a lot of say in it. Thank you.
Well, we do there's a whole flow chart of input. It's very complicated, lots of different input. Like I said, there's the antecedent conditions, what the inflow rates are, what is the current stage now. So, for instance, if Lake Okeechobee is already high and there's a lot of flow coming down the Kissimmee River into Lake Okeechobee, it doesn't matter whether we say we're going to get some more rain or it's not going to rain anymore. The lake's already high and you already have inflow coming in. And in those situations, whatever our forecast for the next week or two oftentimes is overridden by those other factors. Other times, the outlook of what's being forecast is one of the primary reasons that they make decisions. So it depends on the situation. So we can't always get our way every time. Yeah,
Yeah, I'm trying to learn that. Thank you.
sure.
so Mr. Chair, if I can.
Mr.
maybe add
Mitnick,
a little
please.
bit more to that. Thank you. Ms. Thorolipish, so yes, the meteorologists are featured very prominently in our weekly discussions. We have at least a minimum of 2 meetings a week. As we've talked about in the past, how we go through our weekly decision making on all parts of the system, not just Lake Okeechobee. But at least 2 of those meetings, the meteorologists are the ones that kick off the conversation. We start with a whole overview of the weather, similar to all the products that have been in this presentation here today. And then obviously during more intense rainfall periods, we'll talk with a meteorologist multiple times a week. And that's just as a much larger group. The interaction between the meteorologists and the water managers is much more dynamic and fluid on the fly. They're located right next to each other in the building. So they can just easily walk over and have a conversation about what they're seeing, those kinds of things. As Eric said, when it comes to Lake Okeechobee, as the schedule was formulated or as it was pieced together, and it's much the same way as LOSUM will be. It's looking at the overall long-term performance over all these climatic conditions. And currently in the LOR schedule, there are those boxes in the decision trees, as Eric referred to, that bring in some of that climatic data about the tributary conditions and how much water may be flowing into the lake, what that long 3-month outlook looks like that I present to the board every month. All those kinds of things are in the decision-making process. But we absolutely rely on the meteorologists in real time in making decisions throughout the system.
Thank you so much. And I see that you use their charts all the time.
Yep, that's who I steal them from.
Thanks, Mr. Mitnick. If there's no more board comment, we'll go over to public comment now. And if you'd like to make a comment, use a *9 to raise your hand if you're on a cell phone, and *6 will mute and unmute you. And I'll turn it over to Rosie.
Thank you, Mr. Chairman. I do not have any raised hands. Mr. Chairman, I'm sorry. Gary Ritter is recognized to speak.
I figured if you gave him long enough.
Hi, everyone. Eric, great presentation. I know my boss is up in Gainesville is very jealous because he calls himself a meteorological geek and he loves this. So I'm going to, hopefully this will be recorded so that I can send it to him. I have a number of questions, but I'm just going to give you one. When you talk about evaporation rates on Lake Okeechobee, during the highest parts of the year, which I think are March and April and maybe May, where you get your highest evapotranspiration rates, do the rates differ at all based on what level the lake is? In other words, if the lake was lower, would you get higher rates? And if it was higher during those periods, would you get lower rates? Or do you get the same amount of evapotranspiration regardless of what the lake level is?
Okay. I answered that. Is that right? Just making sure.
Yeah, this is a comment period, but that's a great question. So go ahead.
Okay. Yeah, the evaporation rate out of the lake can vary with the depth of the lake. In the very deep part of the lake, it's not going to affect it. In the littoral zone over on the southwest side, if you have very shallow water, particularly with vegetation in it, you're going to get higher evaporation rates from sun because it gets very warm. You can think of that if you have a deep, like Lake Tahoe, 1,000-foot deep lake, the temperature hardly varies through the year, but or through the summer. But then in a very shallow pan of water, it'll get very hot in the afternoon. So the shallow parts off in the southwest part can get warmer, have more evaporation going on. But then if the lake is completely full and deep enough that the light's not really penetrating any further all the way to the bottom, then the variable rate and the height no longer is important. I guess it's important, but isn't a factor.
All right, thanks, Eric.
Mr. Chairman, there are no more hands raised.
Great. Well, thanks very much, Mr. Swartz. That was a great presentation. I think we all learned something from it. I think this is being recorded, so hopefully people can refer back to it if they want to watch it. Weather affects all of us. That's why we're always so interested in it. And I really thank you for an excellent presentation. I thank the board for joining us and the public for joining us as well. And I'll go ahead and adjourn this. Thanks.